Miss Dubois is at the Army 10 miler and she's trying to do her best to complete the 10 miles. She runs 3.5 meters per second for 6,570 seconds at an angle of 165 degrees from the starting line, then turns at the Pentagon and runs 3.2 meters per second. She's kind of tired by this point. For 3,180 seconds at a 290 degree angle. What is Miss Dubois' displacement and direction from the starting line? So I will actually be running the 10 miler this Sunday, October 10th, so wish me luck. But I thought that I would give you guys a relevant problem anyway. So what we need to do first is solve for, since it's asking for displacement, we need to solve for our displacement up front. So if we're given a velocity and a time, we know that, and we're going to assume that our velocity is constant because it doesn't give us an initial or final velocity. We'll assume that our displacement is just velocity times time. So for the first vector, actually instead of x, we'll call this the change of our vector 1. It'll be 3.5 times 6,570. And we get, let's see, 3.5 times 6,570, 22,995. So 22,995 meters. Okay, and then our second vector, vector 2, will be the velocity times time for the second part, which is 3.2 meters per second, which is a little bit slower because I'm assuming I'll be a little bit more tired by that point, times 3,180 seconds. So we'll go ahead and multiply those two numbers together. And find our displacement for the second vector, which is 10,176 meters. Alright, so let's go ahead and just draw a little picture of what's going on. So we have this 22,995 meters, and it is at a 165 degree angle. So we know that 165 degrees is past 90 degrees, but not quite to 180. So we're going to be going off in the second quadrant, probably a little bit closer to 180, with a displacement of 22,995. And again, our direction from 0 is 165 degrees. And then we have our second vector, which is 10,176, but it's at 290 degrees, which 270 would be straight down, so 290 will be just a little bit past that. And since we have 10,176, it'll be about half of our first vector. So we'll go ahead and label this 10,176 meters. And what we are looking for is our resulting displacement, this guy right here. And we know it should be roughly somewhere in the second to third quadrant range. We'll actually have to break down our first vector and our second vector to figure that out. So for our first vector, our x1 will be equal to our hypotenuse cosine 165. Okay, so making sure that you are in degree mode, so go to mode, make sure you're in degree. You're going to say 22,995 cosine 165, and you get negative 22,211.5. So negative 22,211.5 meters. Alright, your second x displacement, so x2, actually, yeah, we'll do that in blue since our second vector was blue. Okay, it'll be 10,176 cosine our theta, which was 290, and we get 3,480.4. So 3,480.4 meters. Alright, so before we do our x total, we should look at our vectors. Okay, our first one went to the left, so it should be negative, which it is. Our second one went back to the right a little bit, so it should be to the right a little bit, positive, so which it is. So to find our total x displacement, we're going to add ours up. So negative 22,211.5 plus 3,480.4, and we get negative 18,731.1 meters. And then we'll do the same for the y. So to figure out how far up our first vector went, we're going to say that y1 is equal to hypotenuse sine theta. So our hypotenuse was 22,995 sine 165. And we get 5,951.5. So 5,951.5 meters. That's a comma right there. Y2 will equal this second hypotenuse sine our new angle, which was 290 degrees. And it should be negative because we went down. So let's go ahead and double check that. So 10,176 sine 290. And we get a negative number. So negative 9,562.3. Negative 9,562.3 meters. Let's double check that I copied that down right. 560. Alright, so to find our y total, we would add these two together. So our y total will be 5,951.5 plus negative 9,562.3. And we get negative 3,610.8. meters. So we know we went to the left 18,730, let's see, what did I do there? 31.1 meters, and we also went down 3,610.8. So this first one is our x component. We went to the left 18,000, and then we went down 3,000. So to figure out how far r is, we're going to use the Pythagorean theorem, a squared plus b squared equals c squared. So we know that our resultant, if we were to rewrite this, we know our resultant will be equal to the square root of, and if you're going to use a negative, guys, put it in parentheses. So we'll write negative 18,731.1 squared plus negative 3,610.8 squared, and then we'll take the square root of that. So negative 18,000, and you want to put it in parentheses if you're going to use the negative. Okay, and we get this huge number. I like to store it as our x value and then take the square root of x. And we get 19,075.95. So we'll go ahead and call that 19,076. So our r equals 19,076 meters. Our direction will be the inverse tangent, because we have our y and our x now, of y over x. So you want to make sure you're not putting your x over your y, that you're doing your y over your x. Okay, so I'm going to say inverse tangent of negative 3,610.8 over negative 18,731.1. Put that in. Okay, it gives me 10.9 degrees. 10.9 degrees is actually in our first quadrant. It's something like this. Okay, so it's giving us that little tiny angle from 0, 10 degrees up. Alright, so we should be pretty familiar. We're in the third quadrant. Tangent is thinking that we're doing the opposite. A negative over a negative is a positive, so it's the same as this 10.9 degrees here. So what we have to do is take that 10.9 and add 180. So 10.9 plus 180 degrees, and we get 190.9. So our actual direction is 190.9 degrees. And that solves for our displacement and direction from the starting line.